Okay, now we are moving on to the part 3 questions. These are 4 points each. And let's start with 32. Quadrilateral NATS has the following coordinates, and we want to prove it's a rhombus. So I have already gone ahead and plotted the 4 points and connected them on my coordinate plane. Even though it does say the use of axes is optional, I like to always take the time to plot the picture just so it's a little clearer to see what's going on. So once we have that, we want to recognize that in a rhombus, all of the sides are congruent to one another. So what I'm going to do is I'm going to find the lengths of all 4 sides. And if we do the math correct, they should all be congruent to one another. Keep in mind that this is not a question. It's not saying, is it a rhombus? We just have to prove it is. So if these 4 sides do not come out to be the same, we have to be doing something incorrect. We made a mistake somewhere. So I'm going to use the distance formula to find each length. So for NA, subtract the x's squared, subtract the y's squared, and this is going to give us radical 50. For AT, subtract the x's squared, subtract the y's squared, also radical 50. If you're unsure how the 50 is coming about, put everything besides the radical in your calculator. For TS, subtract the x's, subtract the y's, radical 50. And last one, subtract the x's and subtract the y's. And we do get radical 50 for all of them. Since this is a proof, we should have a conclusion here. So I'm going to say that NATS is a rhombus since all 4 sides are congruent. All right, moving on to 33. David has just finished building his treehouse and still needs to buy a ladder to be attached to the ledge of the treehouse and anchored at a point on the ground, as modeled below. He's standing 1.3 meters from the stilt supporting the treehouse. This is the point on the ground where he decided to anchor the ladder. The angle of elevation from his eye level to the bottom of the treehouse is 56 degrees. David's eye level is 1.5 meters above the ground. That is a lot of information, but definitely just look at the picture and you can see that you have some right triangles here. And often that means that you're going to be using SOHCAHTOA, or right triangle trig. We have to find the minimum length of the ladder to the nearest tenth that David will need to buy for his treehouse. So the first thing I notice is that there's really 2 triangles in here. So if I look at the initial picture, there's this triangle, okay, 2 right triangles. And then there's the big right triangle. We're looking for the length of the ladder, so that means I'm really trying to find the hypotenuse of the big right triangle. So let's just keep that in mind. I'm going to draw the 2 triangles separate here, just so we can look at them. So if we look at the small one, we know that this is 56, okay, and we know that the base is 1.3. In fact, we know that the base of both of these triangles is 1.3. And we are asked to eventually find this length over here in the big triangle, the hypotenuse. If I start with this triangle over here, notice I don't have enough information. I don't have an angle. There's no way for me to get that hypotenuse right now. So I'm going to start over here on the small triangle. And I'm going to say, let's call this vertical piece X. Based upon that, I can now use SOHCAHTOA. So here's the opposite, the adjacent, the hypotenuse. This would be tangent. So tangent of 56 is equal to x over 1.3. I'm going to cross multiply. X is 1.3 tangent 56. We, of course, have to go to our calculator to figure out what that's equal to. So I got x is equal to 1.927. 3292591. This is not my final answer to the question, so I am not going to round this. Here's how this helps. If you look at the big triangle in the picture, we know that this part, the bottom part, is 1.5, and now we know the top part is the 1.927, so on. So we can now figure out the length of that whole side if we add the 1.5 and that value together. So that comes out to be 3.42732925991. Now when I am looking at this, I can now find, I'm going to use this, I'll call this C over here since it's a hypotenuse of a right triangle. Now I can use the two side lengths to help me find the hypotenuse. When you're looking for a missing side in a right triangle, it's going to be one of two things, unless it's a similar triangle and you have a different type of picture here. But in most cases, when there's angles involved, it's going to be using right triangle trig. Or if there's no angles involved, it's going to be using Pythagorean theorem. And now I can use Pythagorean theorem here. So 1.3 squared plus that whole long decimal squared equals c squared. So I'm going to my calculator, square that, plus 1.5 squared, and then we're going to take the square root of that answer. And when we round this, we are asked to round to the nearest tenth. We get that c is equal to 3.7. All right, our last part 3 question, number 34. A manufacturer is designing a new container for their chocolate-covered almonds. Their original container was a cylinder with a height of 18, diameter of 14. Let's keep in mind that that means that the radius is 7. The new container can be modeled by a rectangular prism with a square base. Okay, so we know the sides are equal. And will contain the same amount of chocolate-covered almonds. If the new container's height is 16, I know this is 16 or 16 centimeters, determine and state to the nearest tenth of a centimeter the side length of the new container if both containers contain the same amount of almonds here. Okay, so let's start with the cylinder. We're talking about volume here. So the volume of the cylinder is, the formula for volume of a cylinder is pi r squared h. We know the radius is 7. We know the height is 18. Over on the rectangular prism side, the volume of a rectangular prism is capital B times H. Capital B is area of the base. So I don't know the sides of the base, so let's just call each of them x right now. So I know the area of that base would be x squared and then times 16. I want to basically get x by itself, so I'm going to divide both sides by 16, and I'm going to put this whole big thing in my calculator. So this is a lot to type in. So I have pi times 7 squared times 18 divided by 16. So I got 173.108295029 is equal to x squared. I want to take the square root of that. And we are asked to round this to the nearest tenth. So I got that 13.2 is our value of x. That means that is basically the side length of the new container. Now there's a second part to this question. It says a store owner who sells the chocolate-covered almonds displays them on a shelf whose dimensions are 80 centimeters long and 60 centimeters wide. The shelf can only hold one layer of new containers when each new container sits on its square base. Determine and state the maximum number of new containers that can fit on the shelf. Okay, so if we think about this, we want to basically imagine that picture a shelf in the grocery store. We're stacking these all on the shelf, okay, and we want to figure out how many can fit. We know the dimensions of how big this shelf is. We know it's 80 centimeters long, and we know that the container is about 13.2 centimeters long. Okay. Then we basically know that the width of the shelf is 60, and we know the width of the new container is 13.2 centimeters. Go back to the picture up here, right? Here's our length. Here's our width. They both are labeled X. That's what we found before to be that 13.2. So if the length of the shelf is 80, let's divide that by 13.2 to see how many we can fit. And I get a little over 6, but we can't put 6.06 containers on the shelf. So we're going to say 6 can fit lengthwise. Over here, let's divide the 60 by 13.2. So I have 4.5454, so on. Again, I can't put a fractional container there, so the max I could fit is 4. So I can fit 6 longwise, 4 by the width. So multiply them together. We can figure out how many can fit there, almost like in an array. And we would get 24 containers. Okay, for our part 4 question, we have a proof. This is a 6-point question, and generally any 6-point question is going to have a good amount of challenge to it. So for 35, we have this complete proof. I'm just going to move the calculator out of the way here since we don't need it for the proof. And it says in quadrilateral ABCD, E and F are points on BC and AD respectively. We are given some line segments that are drawn, and then we're given some angles and segments that are congruent to one another. Okay, so for most, I'm going to say most, proofs on the Regents exam, they often have to do with some sort of quadrilateral. So knowing your properties of trapezoids, parallelograms, squares, etc., is really important for getting full credit on this proof. So again, that's how we are going to try and go about this question here. And it's also key to note that when you are doing a proof, there's often many ways to get the correct answer. So don't worry if you came up with something that's a little different than this. There are different ways to do the proof. I'm just going to go through one option here. Okay, so I have already gone ahead, written down all of these givens, write all of it. It's a lot, but write it all down for the givens. And I've gone ahead and marked everything in my picture that we were told that was congruent. So angle ABG and angle CDG, AB and CD, and then also CE and AF. Since those were just parts of the bases of this quadrilateral here, I just basically like highlighted or bolded over those segments so it was clear what the congruent pieces were. Our goal is to get that FG is congruent to EG. So what I notice here are these two triangles in the middle of the picture, and FG and EG are two sides of them, and they're two corresponding sides. So my goal is basically to get, so these are my goals, thinking about this before I actually write the proof. I want to get triangle BGE to be congruent to triangle DGF, because if I get that those are congruent, then FG is going to be congruent to EG by CPCTC. Okay, so our goal, get those two triangles to be congruent to one another. All right, let's talk about one way to do that. So I noticed that we were given that AB and DC were congruent, and we were also given that these two angles were congruent, and to me, that's key to this question. So if you take a look, I'm going to draw in this Z shape here. A Z shape is key for recognizing alternate interior angles, and if alternate interior angles are congruent, which they are here, right? They told us that in the givens, then you have parallel lines. So let's do this one step at a time. I'm going to say that AB is parallel to CD because if a pair of alternate interior angles are congruent, the lines must be parallel. Okay, and we could say the two lines or the lines cut by a transversal, I'll actually add in here, the lines cut by a transversal are parallel. So in this case, the transversal is BD. A transversal is just a line that crosses other lines. That basically tells me that ABCD is a parallelogram. We knew it was a quadrilateral. Now I know it's a parallelogram. And that's because a parallelogram is a quadrilateral where a pair of opposite sides lots of writing on this proof, where a pair of opposite sides are congruent and parallel. We already knew AB and CD were congruent. We talked about in line 2 how they're parallel. Now I know I have a parallelogram, and I get to use all of the properties of a parallelogram because of it. Okay, if I know that ABCD is a parallelogram, I now know that angle CBD and I'm actually going to change this here, is congruent to angle ADB. And there's a pretty long explanation as to how I know that. So let me just mark off in my picture what I'm referring to. I know that this angle here and this angle here are congruent to one another. And the reason it is because we know this is a parallelogram. That means opposite sides are parallel. That creates that Z shape going the other way. So I'm going to put all that information in reason 4. I'm going to say, since ABCD is a parallelogram, opposite sides and I'll even write which opposite sides I'm referring to. So I'm going to say BC and DA are parallel, and parallel lines cut by a transversal form congruent alternate interior angles. Okay, for line 5, let's think about what else we know about a parallelogram. And we know that opposite sides are congruent. So we've already said that AB and CD are congruent, but we've never actually stated that BC is going to be congruent to DA, and that's because opposite sides of a parallelogram are congruent. And I'll go back to the picture and explain that as well. But that would be what I'm going to include in line 5. All right, let's take a look at the diagram. I'm going to erase the Z shape again just to kind of get rid of some clutter. We just said that BC and DA are congruent. Now, remember before we said that EC and AF are congruent to one another? Let's think about this. If we know the whole segment BC is congruent to the whole segment DA, and we know CE and AF are congruent, if we subtract them, BE and DF are going to have to be congruent. Okay? So it's basically like if I say, okay, these two blue pieces are congruent, the two pink pieces are congruent, then by subtraction, these two green pieces must be congruent. So we have to just figure out, well, how do we actually write that? So let's start off by saying in line 6, okay, that BE plus CE is congruent to AF plus DF, and that's by the segment addition postulate. Basically, we could take two segments and add them up. Okay, and they're two congruent segments, two pairs of congruent segments. And that means that basically BE must be congruent to DF, and that's by the subtraction property or subtraction postulate. Now that I have that and I know BE and DF are congruent, I'm looking at these triangles again and I have these sides are congruent. And now I have two things. So if you want, if the picture's starting to look crazy and think about it, this is a 6-point proof. It's going to be a lot, right? It's not going to be an easy proof or problem by any means. But let's think about it this way. We have these angles marked off. And we have these sides marked off. So I just kind of drew a rough sketch of what this looks like off to the side. So now you can see, all right, well, we have an angle marked off in each triangle and a side marked off in each. Can we get something else so that we can prove the triangles are congruent? And we can. We could talk about these vertical angles in here. So vertical angles are formed by intersecting lines. So let's talk about how they are congruent. So I'm going to say that angle BGE is congruent to angle DGF. And I'm going to explain how I know that. And that's intersecting lines form congruent vertical angles. Okay, you could separate that into two lines if you want to talk about how they're vertical angles, and then the next line they say they're congruent, that's fine too. All right, we are getting there. We're almost done. So I'm going to mark those off in my picture here. And now let's go to our goals that we set in the beginning. We said we want to prove the two triangles are congruent. That way we can use CPCDC. Now I have enough in my little picture here to show these two triangles are congruent. And they're going to be congruent by angle, angle, side. And then we can use CPCDC to finish off the proof. So line 9, triangle EBG is congruent to triangle FDG, and that's because angle, angle, side is congruent to angle, angle, side. And lastly, our proof statement, FG, is congruent to EG by CPCTC. Okay, and finally, we have finished this proof. Keep in mind, as I said at the start of the video, there are different solutions to your proof. You could have some of your steps reordered from mine. This is just walking you through one potential solution. Okay. Make sure you check out the rest of the videos on my channel to see other solutions to Geometry Regents exams.